Okay, so in our yesterday's class, we were talking about your behavior of solutions of ODEs, right? So what we did, we considered the homogeneous second order linear differential equation given by this, okay? And then what we did by some transformation, we reduced this equation into the form like this is equal to 0, okay? And I told you that studying the solutions of 1 is equivalent to studying a solution of 2 at least in the context of the zeros of the solution of 1. Okay, so I told you that the zeros of both these equations, they are going to behave similarly. Okay, and yesterday we were doing two theorems, that is Strum separation theorem. Okay, and we were doing theorem A and B, okay, fine. So if you recall, theorem A was related to the occurrence of zeros of linearly independent solutions of this equation, okay, and what it said that the zeros, they occur alternatively, okay. And in the second case, in the second theorem, so what we were doing that if I consider this equation where your qx is strictly less than 0, qx is strictly less than 0, then what it say? Can somebody tell me what it say?
U has at most 1 0.
U has at most 1 0. Okay, fine. So what we are going to do today, at the beginning, we are going to concentrate on the case where qx is going to be greater than 0. So let us see what happens when qx is strictly greater than 0. Okay, so fine. So this is my equation. U double prime plus qx u equal to 0, where we have considered that qx is greater than 0. Okay, fine. See, suppose I am considering the solution curve. I am considering the solution curve in the xy plane. Okay, so now, suppose I am considering the solution above x-axis. I am considering the solution above x-axis. So I have a curve something like this. Okay, so since I am considering the solution above x-axis, so that means I'm definitely assuming that ux is greater than 0. Is it okay with everybody? Ux is greater than 0. Okay, so now if I look at this differential equation, then this is going to give me u double prime x, this is equal to minus qx. Okay, so now I am assuming that qx is strictly greater than 0, and since my solution lies above the x-axis, the solution is already 0 there. Okay, like say I'm simply considering a portion of the x-axis where I'm going to consider my solution. Is it okay with everybody? I'm not considering the whole real line. Is it okay? I'm just simply considering a small portion, okay, where I am assuming that the solution curve lies above x-axis. Okay, fine. So now, then what is going to happen? So from this expression, it clearly tells you that your u double prime x, it is strictly less than 0. Is it okay with everybody?
Yes, sir.
Yes,
right?
sir.
So now, what is the geometric significance of that about the property of the curve ux in the neighborhood of that particular portion of x where we are considering the solution?
It will be concave down.
It is going to be concave downwards, right? So basically, I should get something like this. Is it okay?
Yes,
Fine?
sir.
Yes, sir.
Okay. So actually, it was pretty easy for me to draw a concave downward curve like that. But if I consider the entire real line, or if I consider a very big interval, like I don't know how, I mean, this curve is going to behave like in the entire interval. Okay. See, the case may be like it may be so that it is going on and on and on like this. It is going on and on like this. Okay. And like say again, it is never crossing x-axis at all, isn't it? I may have a possibility like that, isn't it?
Yes, sir.
Right? See, the way I have drawn the graph here, the function ux, it is monotonically increasing, right? Isn't it? Okay. And the curve is concave downwards. So in order for the curve, despite maintaining its concave downwards property, if it is going to cross my x-axis somewhere, so then what I must have at some juncture, the function must be starting to decrease, right? Must be, I mean, monotonically decreasing, right? Starting to be monotonically decreasing. Is it okay? So if I have this situation, so then there is a possibility that it is going to cross the x-axis somewhere, and then I will be able to claim that the solution has a 0. Is it okay with everybody? Right? I can have these two different scenarios, isn't it? For a, like say for that portion of that curve, solution curve lying above x-axis. Is it okay? Fine. So yes.
Sir,
Yes.
it could have just started in a decreasing fashion, right? There is no restriction on that, right? It could have itself started as a decreasing curve, concave down.
That is fine.
Okay.
Then we are done. Then we are done. But there is no guarantee, right?
Yes.
There is no guarantee.
Yes.
Isn't it? So yeah, it is fine. Say simply consider a curve. Simply consider a curve above x-axis, which I am assuming that it is the solution of the given differential equation, right? Say suppose we don't know anything about whether it is concave upwards or concave downwards. I don't even know whether it is coming from, I mean, this equation or not. Suppose it is a solution of some differential equation, fine, right? So if it is lying above x-axis, the very crucial criteria that which must be satisfied is that it has to be monotonically decreasing at some portion in order to cross the x-axis. Is it okay? Right?
Yes.
Only then the solution is going to have a 0. Is it okay?
Yes.
Fine. Right? So that monotonically decreasing part is a prerequisite for the curve to cross x-axis. Is it okay? Irrespective of whether the solution curve is concave upwards or concave downwards. Is it okay? Fine. So now with these, I mean, knowledge in hand, I would like to move to the next theorem. I would like to move to the next theorem. Okay, so it is theorem. Say, see, I'm simply following. I mean, CMOS. Okay. Say, so this is so let UX be a non-trivial solution of the differential equation is 0, where Qx is strictly greater than 0. Where Qx is strictly greater than 0. Okay, and again, qx is strictly greater than 0. We are assuming that it is along positive x-axis. So that means for all x greater than 0. For all x greater than 0. Okay, fine. Okay, so then if this statement is interesting, if infinity, right? So then ux has infinitely many zeros along. Remember, this is positive x-axis. Okay. See, we are only considering the positive x-axis part. Like say, it's kind of it makes our life simpler. So you may be thinking, why not negative x-axis? See, whatever we are going to prove, so definitely that part we can shift towards left, and then it is going to include something. In the negative x-axis as well. Okay, it is not going to make much of a difference because you can always do some kind of coordinate transformation. So I may consider a new coordinate system, say instead of xy, I may consider it to be something like say capital XY. And for the capital XY, I'm going to use some kind of shift. So then it is still going to be better. Okay, fine. Okay. So how to prove it? Okay. So please have a look at it once again. Because this is going to be crucial. This is going to be crucial. This part is going to be crucial. Okay, fine. Say how we are going to prove it. We are going to prove it through the contradiction approach. Okay, fine. So for that. Okay. Proof. Okay. Okay. So on the contrary, let us assume that your ux has only finitely many zeros over positive x-axis. Okay, fine. So that means what we can do. I'll tell you what I'm doing here. See, suppose this is 0. So this is 1. See, I have roped in 1. Because in the statement of the theorem, so there is an integration going from 1 to infinity, isn't it? Fine. So that is why I have wrote this. Okay. So then what I'm going to do, I'm going to take a point x0. Okay. So now because I have assumed that ux has only finitely many zeros over the positive x-axis, I can always assume that there exists like say x0 which is greater than 1, such that your ux is not equal to 0 for all x greater than equal to x0. I can always do that because I have already assumed that the function ux has only finitely many zeros. Is it okay?
Yes, sir.
Right?
Yes, sir.
Okay. So now what we are going to do, we are going to contradict this. And basically, even if we don't want to contradict it, if somehow I can prove that, your u prime x is negative, that means the function is monotonically decreasing. So then I am done. Is it okay with everybody? Fine. Okay. So because ux is not equal to 0, again as before, without loss of generality, we can easily assume that your ux is greater than 0. Ux is greater than 0 for all x greater than equal to x naught. And again, we could have assumed it to be negative also, but I can guarantee you that you can get to the same conclusion the way we are going to prove the theorem. Is it okay? Fine?
Yes, sir.
Yes.
Okay? Fine. Okay. Now, what we are going to do, see, let me tell you what my purpose. My purpose is that I would like to prove that u prime x is less than 0. U prime x is less than 0. Is it okay? Fine. So, in order to prove that, what I am going to do, because I have already assumed that ux is greater than 0. So, if I have to prove this, so then if I can prove that, that this ratio is positive, my job will be done. Is it okay with everybody? Fine? Is it okay?
No, sir. Can you please repeat?
See, I have already assumed. Okay, I'll go in a different way. Okay, so I have already assumed that ux is greater than 0. Okay, so now my purpose is to prove that u prime x is strictly less than 0. Okay, so in order to prove that, if I can prove that this ratio, because this is always positive, the denominator is always positive. If this ratio is less than 0, then also it will be done, right?
Yes, sir.
Isn't it? So instead of proving that, what I would like to prove that this ratio is positive. Is it okay? Fine. That
Yes,
is where we are going to define a new function v of x to be this. Okay. So what we are going to do now, we are going to define a new function v of x. Ux. Okay, fine. And I'm going to prove that Vx is positive. So now you know the rationale behind choosing a new function, defining a new function. Are you getting the point? Why I have defined this new function? It is only to eventually prove that this is positive, and that is going to make u prime x negative. Is it okay? Fine. So that is what we are going to do. So as before, if you recall, like say, when I prove the Abel's inequality, Abel's identity, so then I was doing something like this. Okay, so I was trying to find out the derivative of that function dx. Okay, so here also I am going to do the same. And now you will see why I am doing this. So this is going to be ux whole squared, then u double prime x ux, then minus u prime x squared, right? Okay, so this is going to be u double prime x by ux plus u prime x by ux whole squared. Is it okay? Fine? Okay. What is this? What is the first term? Yes?
qx.
Exactly. This is nothing but qx. Because my original equation was what? q double prime x plus qx, isn't it? Right? From there, this is qx. Fine? And what is this?
Minus Vx.
Yeah, or simply your Vx squared. Isn't it? Fine?
Yes,
Okay.
sir.
So now, if I integrate v prime x between x naught and x, whole square, and from here, just a minute, what I can do, I can simply replace this. Eventually by Vx minus Vx naught, isn't it? Is it okay? Fine. Okay. So I'll simply write from here. I'm going to simply write. I'm sorry for you because I mean you have to write it down in your notebook or whatsoever. But I can simply erase it and I can modify it from here. I'm going to get. I can write it like this. Is it okay? Fine. Yes.
Yes, sir.
Isn't it?
Yes, sir.
Yes, sir.
This is x is the upper limit, right? That is a variable, and obviously this being the upper limit, I'm assuming that it is of the right side of x naught, right? So now my aim is to prove that Vx is always positive. So if I take your x sufficiently large, so whatever may be, sorry, this is Vx naught, not P naught x. Okay? Whatever may be the value of x, so obviously this is going to, as I let x tending to infinity, this is going to go to infinity. Is it okay? This is always positive. This is always positive. And whatever may be the value of this, I can always get Vx to be positive. Is it okay with everybody? Because of this infinity. Isn't it?
Yes, sir.
Yes. So that is why what we are going to have from here, I am going to get u prime x strictly less than 0. That means it is monotonically decreasing. And again, under the assumptions, like say, just a minute. If I use this, so because I assume that ux is strictly greater than 0, so that means this is going to be negative. So that means the curve is going to be concave downwards, right? Curve is going to be concave downwards, and then since u prime x is strictly less than 0, right? The function is monotonically decreasing. So that means at some points towards the right of x naught, the solution curve is going to cut the x-axis at some point. Is it okay? Fine? Is it okay?
Yes, sir. Yes.
Right?
Second.
Now, so this gives you an idea that from every existing root, existing zero, I can produce as many new zeros as I can. Isn't it? Say, I have found a 0. Say suppose the new 0 to this concept I have found, say suppose that is x1. Right? Again apply this concept. Isn't it? Again apply whatever we have done for x. Now whatever role x0 played, now do the same for x1. That is going to create another 0. Is it okay? In this way, we'll be able to produce infinite number of zeros of the function ux. Clear?
Yes.
Yes. So similarly, see, so far I have been telling you that okay, I have assumed ux to be greater than 0, and I told you that I mean if I had taken this as negative, so then also we could have easily proved it. Okay, so just simply look at this. If it is less than 0, so then obviously this is going to mean that u double prime x is positive. So that means the function is concave upwards. Function is concave upwards. Because I have assumed ux to be less than 0, I am going to start with a solution curve which is below x-axis, isn't it? Right? So then I am simply going to prove that u prime x is greater than 0, so that the function is monotonically increasing and it is going to cross the x-axis somewhere. Is it okay with everybody?
Yes.
Right? So in either way, it is going to work. Okay, you don't have to, I mean, necessarily assume that ux is positive above x-axis. Okay, you can do that in that way. Okay, fine. So this is about your.
Sir, what is the domain of u? Is this x greater than 0?
Yes, 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 yes.
Okay.
Because see, you may be asking me why it is so. Like say, whenever I mean, we consider some interval, we always move from left to right, isn't it?
Yes, sir.
We always move from left to right. So that is why, if you take it along positive x-axis, your.
So this is not on the entire real line.
Say, although they are saying that it is only along positive x-axis, but for me, I'm not sure. For me, I think this can be applied towards the negative x-axis also, because you can always use some kind of shifting. Okay, but if you want to stick to the theorem, yes, it is only along positive x-axis. Okay.
So, sir, can you say something about the integration part? So this is integration 1 to infinity qx dx equals to infinity. So can you something about the behavior of this integration?
So
Why
maybe
this is
I'm
so
going to
important
do
here?
a couple of exercises. Okay, I'm going to do a couple of exercises, then it will be clear to you. Is it okay? Fine?
Okay.
Again, see, that the behavior is going to depend upon the integrand, isn't it? Behavior is going to depend upon how qx behaves. Is it okay? Right? So, depending upon that, you are going to bring out your conclusion. Okay? Fine. So,
sir, we are integrating over 1 to infinity. So what is the importance of 1 here?
No. again,
Why you are
yes, yeah, one is misleading. I'm telling you that it is going to work for any positive number. Don't worry about it.
Yes.
Yeah, I think like this is the way Simmons did. So I mean, everybody is following that. Okay, so now let us try to do one exercise. X squared y prime. Okay, let us consider this equation. What is this equation? Does it ring a bell? You forgot it? Special function, something like that?
Basic function.
Bessel's function. Bessel's equation. This is Bessel's equation, right? This is Bessel's equation. So now, just a minute. Okay. Okay, so if I reduce it to normal form, it is going to look like this. And then from here, you know that Qx equal to 1 by x and Qx, capital Qx. So this is equal to 1 by p squared by x squared. Okay, fine. So now, if I want to reduce it to this form, if I want to reduce it to this form, okay, so then what is going to happen? If you recall, this Qx was what? Obviously, I recall this. Then there was something like, I think minus. Right? Is it okay? Fine. So from here, Qx is 1 minus p squared by x squared. Then p prime x, this is minus 1 by x squared, right? So this is going to be plus 1 by 2x squared. And then this is minus 1 by 4x squared. Is it okay? So this is going to give you 1. And from here, see, this is half minus 4. This is going to be 1 by 4. So, pass. Okay. Yeah. I hope I'm fine. Is it okay? Am I correct? Fine?
Yes, sir.
Okay. Fine. So what I have done, I have reduced this Bessel equation into this form, where this Qx is given by this, Okay. So now, if I look at this expression, if I want to perform your 1 to infinity Qx dx. Okay, so then this is going to give me 1 to infinity simply dx, and then from here plus 1 minus 4p squared by 4. So maybe I can simply write it as something like this. Anyway, yeah, I should be okay. Okay, fine. Is it okay? So obviously from here, I mean, for a finite value of p, this is always going to give me infinity, isn't it? Is it okay?
Yes.
This is always going to give me infinity. So if I use that theorem C, so then what is going to happen? According to that, this Bessel function is going to have infinite number of zeros. Yeah, because the solution of this equation is nothing but the Bessel functions, isn't it? Right? Isn't it? So this equation, the solution, all those Bessel functions, so they are going to have infinite number of zeros. So that is what the exercise is all about. So you have to prove that. You have to prove the earlier theorem to prove that every non-trivial solution of the Bessel equation has infinitely many positive zeros in fact. Okay, because I am considering that in theory x along positive x-axis. And you can easily see from here, that whether I have taken it as 1 or some x naught greater than 0. If I instead of 1, I have plugged in x naught, which is greater than 0, still it would have 1. Is it okay? Fine. So, like I said, that 1, it is simply like some kind of ornament. Don't worry about it. It is ornamental. So it is that. So now this is a really interesting example, and this is related to the last exercise that I had told you yesterday. So now I am considering this function. I'm considering this equation. Okay, right? So here you have to prove that every non-trivial solution has an infinite number of positive zeros. Infinite number of positive zeros if k is greater than 1/4, and only a finite number of positive zeros if your k is less than or equal to 1/4. Okay, right? So the exercise is about, this is nothing but the Euler equation. Okay, this kind of, Cauchy Euler equation. Fine. See, this you can easily do because yesterday I reached a conclusion that if I want to solve this equation through the transformation, x equal to e to the power t. So eventually it boils down to finding the roots of the auxiliary equation. I think it was 1 plus minus 1 minus 4k, right? 1 minus 4k by 2, something like this. Yes?
Yes, sir.
Yeah, because m squared minus m plus k. I think I'm fine. Okay, so now obviously you can see that, if k is strictly greater than 4, this is going to have some complex root. Isn't it? This is going to have some complex root. So if it has some complex root, so then it is going to be of this form, isn't it? The solution is going to be of this form. Your y equal to what? This is okay. Something like a sine or cos, whatever. Some function, isn't it? Some function of t, and that t you can easily convert it into x. Is it okay?
Yes.
Are you getting my point?
Yes.
Right? Fine.
Yes, sir.
And if this is so, then it is going to have real root, and then your solution is going to be of this form, like c1 x to the power m plus c2 x to the power minus m. Isn't it? Right? So because it is in some polynomial form, obviously this is going to lead you to finite number of zeros of y. Is it okay? Or for that matter, the solution of that equation. Okay? And when your k is strictly greater than 1/4, because this is some cosine function, you know that the graph of that function, it is going to cross x-axis at infinite number of points, right? I don't even have to show it. I don't even have to give you the explicit expression. You can simply say that it is going to be a sine or cosine function. That's it. Is it okay with everybody? Right?
Yes, sir.
Okay. So now you may be thinking why I am roping this in this particular example. So from here, you can see that if I take this is nothing but my small qx. So if you do this k by x squared dx, right? Again, as before, what I am going to get, it is going to give me 1 by x, and then this, isn't it? And this is not infinite, right? Are you getting the point?
Yes.
Yes.
This is not infinite. Right? Like in theorem C, what it say? Like your that qx, and of course, say here, obviously qx is strictly greater than 0 for all positive x, right? Qx is strictly greater than 0 for all positive x. And from there, I have found out that this integration does not lend you to infinity. But despite that fact, I have found out that for k strictly greater than 1/4, what I get infinite number of zeros of the solution of the given differential equation. Right? So that means what is happening? This theorem C, it is what? A sufficient condition for the existence of infinite number of zeros in the positive x-axis. Not necessary. Clear? Okay. So I hope I have been able to answer your question, like say the nature of that integral. As I have told you, I mean, it is going to depend upon what the integrand is. That is nothing but what the function qx is. Okay, fine. So, how much time do I have? Okay, I think I'm going to fine. Now I will be coming to, three theorems pertaining to this Strum Comparison theorem. Strum Comparison theorem. Okay, so I'll do the theorem, and after that I will tell you about the significance of this. Okay, so here suppose I'm considering this. Okay, so let me call it 1. So here theorem. So this is A, theorem A. Okay, so if your y-axis is a non-trivial solution of 1 in the closed interval, AB, then y-axis has at most finitely many zeros. I don't know whether they use many or not. Many, let us not use many. Finite number of zeros, simply like finite number of zeros. Okay. Again, finite number of zeros, obviously in that interval, in AB. Right? See, here they are not even concerned about they're not even concerned about the property of small qx. They don't tell us whether qx is greater than 0 or less than 0. Okay, so the proof is very straightforward. It is 2-line proof. Sorry, proof. So the proof is again. So again, it is going to be by contradiction. So what we are going to assume that, let us assume that the solution of 1 has infinite number of zeros in the interval A. Is it okay? Infinite number of zeros in the interval AB. And suppose those infinite number of zeros form a sequence xn. Okay, in AB. Right? Okay. So now, do you recall Bolzano-Weierstrass theorem? What was that? Bolzano-Weierstrass theorem. Every
sequence has convergence of sequence.
Convergence of sequence. Okay, fine. See, now AB is a closed interval, isn't it? AB is a closed interval. So that clearly means that Xn is a what? Bounded sequence.
Bounded sequence.
Right? So there must exist a point x naught belonging to AB such that your xn not equal to x naught and your xn tends to x naught, right? As n tends to infinity. Okay, fine. So then what is going to happen? Your y x naught. So this is going to be limit your right by the continuity of y. I can always use that. Is it okay?
Yes, sir.
And what is y xn?
Is 0.
0, because xn's were nothing but the zeros of the function y, right? And then again, if I want to compute your y prime x naught, so this is simply limit xn tending to x naught, your and this is equal to this
0.
0, because I have already found out that y x naught is 0, so this is equal to 0, right? And from these two statements, what do you get? What do you get?
Y is equal to 0.
Yes, y is equal to 0 by
Theorem.
uniqueness
By
theorem, right? So yes, these are nothing but the initial condition for a second order differential equation, isn't it? Which provides you a unique solution. Fine, which provides you a unique solution. So because y equal to 0, I mean it is the trivial solution is already a solution. So this unique solution must be the trivial solution, which is a contradiction, right? So that completes the proof. Okay, fine. So now, yes. So now I will come to the actual comparison theorem. So in fact, although I mean Simons has described this under the notation comparison theorem, but the actual comparison theorem is going to start only now. Okay, fine. And let me tell you what is the motivation behind that comparison theorem. After that, I'm going to proceed, and you will see that it's just like what we did earlier. Something. Okay. Maybe I will write down this theorem here. Okay, so then. So before that, let me tell you the motivation behind this comparison. See, earlier, you had seen that. Say, suppose I had taken this differential equation, and suppose I had considered this differential equation. Okay, so then you have seen that both of them, I mean, they are linearly independent solutions. They were of the form sin x and cos x, right? And again, you saw that for this equation, I mean, my solution was something like this. Okay, whereas for this equation, my solution card was something like this, something like this, something like this. So that means the solutions of this equation, they had more number of zeros than the solution of this equation. Is it okay? Fine. So now let us see whether through some theorems you can establish some fact like this, that it is always going to have, I mean, more number of solutions. Now the thing is here, because this q was constant in both the cases, then I mean we could straightforwardly make some conclusions, right? How many zeros what will be the distance between those zeros? Those we could have easily done. Now, instead of qx being a constant, if we use it as a variable, let us see what happens. Okay, so this is what this comparison theorem is going to tell you. Okay, so let your yx and zx be non-trivial solutions of the differential equations. Like this, first one is y double prime plus qx y equal to 0, and the second one is j double prime plus rx j equal to 0. Or let me call it 1, and let me call it 2. Okay, fine. And again, another thing here, we are assuming that both your qx, rx, they are strictly greater than 0. They are positive part. They are strictly greater than 0. Okay, and we are also assuming that your qx is strictly greater than rx. Qx is strictly greater than rx. Okay, so then the theorem says that then yx vanishes at least once between two successive zeros of jx. Two successive zeros of jx. Yeah. At least once between any two successive zeros between zeros of jx. Okay. Do you find some similarity between this one and something that you have already learned? Yes. You will find some similarity. Yes. Tell me whether you find some similarity between this theorem and some theorem that we have already learned.
If y1
Yes.
and y2 are the two Li solutions
Uh-huh.
of a differential
Yeah,
equation,
yeah.
then
So then,
yeah,
I mean,
the zeros are alternate.
Yeah, zeros occur alternatively, right? Okay. The only difference here is that now we are considering two different differential equations, isn't it? We are considering two different differential equations, and I am considering their solutions. And that is the first thing. That is the first difference. And the second difference is that earlier, if you recall what I did yesterday, like say between two successive roots, there was only one zero. I mean, between two successive zeros, there was only one zero of one of the linear independent solutions, right? But now this theorem is telling you that yx vanishes at least once, right? So that leaves you with the possibility that it may have more than one zero. Is it okay? The difference between what we learned earlier for the linearly independent solutions and this one. Is it okay?
Yes, sir.
Right? Okay. Fine. Okay. So, it will be similar to the previous one. In fact, the same methodology you could obtain, adopt. But here, I'm going to do it slightly differently. But that will also work. Okay. So, let x1, x2 be two successive zeros of Jx or J. J. Okay, so then you're definitely Jx1 equal to 0 equal to Jx2 Fine. That is the first thing. And the next thing is that why? Why is that?
Because we are taking successive zeros.
Yes, because if J, sorry, this is not Z, this is X. If X is such that Zx equal to 0 in this interval, so I'll have another 0 in between. Is it okay? Fine? Okay. So now let us assume that Y doesn't vanish in that interval. Let Yx not equal to 0 for all x belonging to x1, x2. So I am going to write a contradiction, and then my job will be done. My job will be done. And as before, since y is not equal to 0 in that interval, what we can assume that either y is positive or y is negative. Is it okay? Fine?
Yes.
Right? And even because I have assumed that z is not 0 in that interval, again, z can be either positive or negative. Isn't it? Right? So I can choose any combinations like z is positive, y is negative, both z and y are negative, and z is negative, y is positive in that particular open interval x1, x2. But any combination is going to work. I'm guaranteed. Right? So without loss of generality, what we can assume that both yx and zx both are strictly greater than 0 for all x in that interval. Okay, fine. And again, let me tell you that if you consider the Wronskian of yj, which is given by your yj prime minus y prime j. Okay, so let me call it 3, okay, right? So then obviously you know that this 3, it is going to reduces to this simply yz prime at x1 and x2, isn't it? Is it okay with everybody? Fine. Is it okay?
Yes, sir.
Yeah. Is it the other way or just a minute? Yeah. No, because J vanishes. J vanishes at x1 and x2, so that is why it reduces to this. Okay, fine. See, now from here, I could have exactly proceeded like the way I had done in proving the earlier theorem. That will also work. Let me guarantee you. But let us try to do something else here. Let us try to do something else here. So then, okay, fine. Don't worry about it. This here, this statement. Let me call it key or something like that. I'll come back to this again. Okay. Okay, so now look at 3. So if I look at 3, so then if I find out w prime, of course, this is a function of x, w prime x. So this is going to be as before. This is y j double prime minus y double prime j. Because see, you are going to have y prime j prime from here, and from here also you are going to have y prime j prime, and they are going to cancel out each other. Is it okay? Fine?
Yes, sir.
Yes? Okay, fine. So now, okay. What is J double prime? Isn't it? Minus Rj, right? And what is Y double prime? Minus Qy. Is it okay?
Yes, sir.
Fine. So this is going to give me your Q minus R Yz. Okay, fine. See, now at the very beginning, I had, this in the statement of the theorem itself, Q was greater than R, right? So that means obviously this is greater than 0. Q minus R is greater than 0. Okay, and then since both Y and J, I was assuming them to be positive functions. So that means your okay, fine, isn't it?
Yes, sir.
So this implies if I integrate it between x1 and x2, that will be also greater than 0. Yes, fine. And if you integrate this, what you will get? If you integrate this, what you are going to get? You are going to get w x2 minus w x1. Okay, so this is greater than 0, right? So this will imply w x2 is greater than w x1, right? So let me call it what? Say B. Let me call it B. Okay. So now, as I have told you, let me now go back to A. Let me now go back to A. Okay. So now let us see what happens. What happens to this at x1? Okay. So now from here, if I want to compute wx1, this is yx1 and j prime x1. So what do you get out of that? Yeah. What do you get from there? Okay, so maybe I will draw something for you, and then it will be clear. See, what I have assumed that at x1 and x2, right, your j vanishes, and I have also assumed that the j is a positive function in the open interval x1, x2. So my curve here, it is going to look like this. Agree? Yes?
Yes,
Okay.
sir.
Yes, sir.
And so this is z dash, and I have already assumed that in this interval your y is always greater than 0, right? So under those assumptions, wx1, this is equal to y x1, j prime x1, what it will be? It will be positive or negative?
Negative.
Why?
So
It will be?
Positive.
It will have to be
Positive.
positive because here j must be a monotonically increasing function, isn't it? Is it okay?
positive.
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 So this is going to be greater than equal to 0. Similarly, y x2 is less than equal to 0. I don't want to do this. You know why it is. Is it okay? Fine?
Yes, sir.
So
Yes.
that means I get a contradiction from here because this is going to give me what? Wx1 is greater than equal to Wx2 unless they are equal to 0. Right? Unless they are equal to 0. Isn't it? But they cannot be equal to 0 because I'm assuming that, y and z are non-trivial solutions. Isn't it? Fine? So, y and z being non-trivial solutions, can it be 0? Wronskian. I can always assume them to be linearly independent solution of some equation. Isn't it? Right? So in that case, your W cannot be 0. So what is going to happen that in either case, I am going to get a contradiction. Right? I am going to get a contradiction. So that means yx must vanish. Yx must vanish in the interval x1, x2. Okay, fine. So now, okay. Now, what is the application of this? I'll just give you again that Bessel's equation example. So what does it tell you? So basically, if okay, so basically it tells you that the differential equation having qx as coefficient, it is going to have more number of zeros, right? Than the one having rx. Okay, so now, okay, 1 minus. Okay, so now if I want to compare the zeros of the solution of this equation and this equation, what can you comment? What can you comment? I know that the solution of or maybe should I make it more complicated? Yeah, maybe I'll make it more complicated. Yeah, I can make it more complicated. But before that, let me try to walk this up. So obviously you know that here, the distance between two successive zeros is pi, isn't it? Is pi. This distance, this is pi. So then from here, what can you say about that? What can you say about that? Yes? See, here your qx is 1. Is it okay? Fine. So then, if I want this, say, suppose I am considering it as Rx, this is 1, and Qx, this is Qx. Okay. So if I want Qx to be greater than Rx, then what I must have? Is it okay? Fine. So from here, I am going to get and of course, I'll tell you one thing. So If I consider only positive P. Is it okay? Fine. So from here, what you can say that definitely for this, for value of P lying in this interval, what?
The second one has more number of zeros.
Second one or first one?
First one.
Second one or first one? First one has the Bessel's equation. The solution of the Bessel equations, it is going to have more number of zeros. Is it okay?
Yes, sir.
Fine.
Yes, sir.
Fine. Yes. So that brings me to theorem C. What I'm going to do, I'm simply going to show you theorem C. I am leaving it to you as homework. I'm leaving it to you as homework. I think. Yeah, so this theorem says let ypx be a non-trivial solution of Bessel's equation on the positive x-axis. So if p lies between 0 and half, of course you can take the value of 0 as well, then every interval of length pi contains at least one zero of ypx. Okay, because from the previous theorem we have already seen that, isn't it? If p equal to half, then the distance between successive zeros of ypx is exactly pi. And if p greater than half, then every interval of length pi contains at most one zero of ypx. In fact, I mean the outline of the proof I have already told you. Okay, outline of the proof I have already told you. I hope you will be able to work it out. It is just writing down the stuff systematically that I have just told you about. Is it okay? Fine. So now I will just get back to. I'll just get back to this one. What was that? Okay, so now from this equation, can you comment upon the nature of the solutions? Okay, so simply by comparing this equation with this one, this equation with this one, I'm leaving it as a homework. Okay, what you should try to do, whatever earlier conclusion we arrived at. Okay, so that means k strictly greater than 1/4. 1/4. This equation has infinite number of solutions. Infinite number of solutions, and k, it has finite number of solutions. Finite number of solutions. Okay, so by making use of the theorems that we have discussed today, I want you to work this exercise. Of course, this I have taken from Simmons. Okay, so if you want to look at it in more detail, you can, just follow Simmons. Okay, so then I think I'm going to stop today's class here. Okay, and yes, I'm going to meet you next Tuesday, not Monday. Okay, fine.